Okay, so now we're going to actually figure out how do we test, is there a difference in what entrees based on changing the music, right? So we're going to use this chi-square test for homogeneity that we talked about. So how do we set this up? We're going to use state, plan, do, conclude. Hopefully you haven't forgotten, but there'll be time for you to remember. Don't worry if you've forgotten your state, plan, do, conclude format. So how are we going to set up our null hypothesis? Remember, null is always there's no difference, that it's either equal or same, just like how in goodness of fit it was that there was no difference in what they expected and observed. And so now there's no difference in the distribution of some variable based on some population or treatment, which in our case is the music. And then HA is just that there is a difference. So you just write those exact sentences, you just put the context, and then you write down your alpha, which if they don't state it, 0.05. So our plan is the same setup, right? So, well, we got to write down our name. So our name would be chi-square. Now it's not goodness of fit, but it's for homogeneity. Make sure I spell that right. Another word, because in your calculator it's not going to be homogeneity, so you could write that down, or I should have given myself more room. You could have also wrote, I'm going to write it above, chi-squared two-way test. So that two-way test is actually going to be more generic, because it's also going to apply to independence tests, which we're not going to get into, but this is more specific. That is what you're going to go to in the calculator. So that's the name, the method you have to write down, especially if you do everything in the calculator. Your conditions, you should make sure that you remember these. You shouldn't really need me to fill out this part, but you need to be random, right? So you need a well-designed, ooh, that's a typo. It's not supposed to be well-designed right there. It's supposed to be from an independent, random sample. So data comes from an independent random sample or from a randomized experiment. So either random sample or random experiment, random treatment. 10% is if you're sampling without replacement. Remember, you don't need 10% for experiment. Is that your sample size is less than or equal to 1/10 of the population. And then your large counts is the same as goodness of fit. It's the same all throughout chi-square test. It's that all expected counts are greater than 5, greater than or equal to 5. And don't forget, you have to actually show them. So how do we know our expected? Because if you think about it, and that conclude is also supposed to be down here. Everything got shifted a little bit. But if you think about, we don't have expected, like if we go back to this, so we have a formula, because when we did goodness of fit, there was some claim distribution and you could find the expected count. Here it seems kind of random, but the formula to know your expected count for each variable is you do the row total times column total divided by table total. And that's just a formula to give you expected count for any two-way test. It's something you have to memorize. It's not on your formula chart. I will show you a way you can get them in the calculator, but they could form a question where you need to know that formula. So it is worth memorizing. So you got to do that first, so you can make sure they're all greater than 5. Get your chi-square value. Once you get all your expected, right? That's the same. And then you find your p-value by finding the area of your chi-squared, which is the same thing as before. Let's review that. Y'all remember the distribution for chi-squared? I ask y'all questions like you're here, but I hope you answer back to me even though we're not in the same room. It's skewed right, and it starts at 0, and then you put whatever chi-squared value and you shade to the right. So I'll say chi-squared was right there. We would shade to the right, and that's your p-value. Now your degrees of freedom, if you remember, when for goodness of fit was your number of categories minus 1. And now that's a little different. Now it's number of rows minus 1 times number of columns minus 1. Again, kind of a random formula that we're not going to get into the proof of why. But you do need to know that also. And again, your calculator will give it to you. But you need to know the formulas in case they form a question. Now I will say this is without the totals. So when you see a two-way table and they have the total columns and rows, you don't use that without total. Say totals. And then you make your conclusion the same way we always do. So I'm not going to read that out loud. But it's going back to, we're either rejecting or failing to reject, and we're trying to see, do we have convincing evidence that there's a difference of some categorical variable across different populations or treatments. So let's do that same example about the entrees and the music and see if it kind of matches what we thought here. So what conclusion would you draw based on the background music influencing? So we're going to start with our state. So HO would be that there is no difference in the distribution of what? Our categorical variable is the entree choice. So there's no difference in the distribution of entree choice. Let me see how this is worded. Across, for different musics played. I'm trying to make sure I match this setup we have. So we said there's no difference in the entree chosen for, and then what was our different treatments was the music played. For different background music played. Okay, so then HA is always easy. Once you can form your HO, your HA is easy. It is just there is a difference, and then you repeat the same thing. Your null is always no difference. There is a difference. Music played. And then I'll go and write down my alpha over here, 0.05, because they didn't tell me. Okay, so that's state. Now let's do plan. So I'm going to go and write down my name, which again, you could write down either one. Chi-squared two-way test. I'm going to write down both just to kind of show you, but you do not have to write down both. Or you could write chi-square for homogeneity. Okay, so we need, first condition is random. So what was random? If we go back to the problem, the researchers recorded, European restaurant compared 3 randomly assigned treatments, the music, French music, and Italian music. So there was randomly assigned treatment. And I would go ahead and show that you know what treatment it was, type of music. Okay, so because of that, we don't need 10% rule, because it was an experiment, it was treatment, not a random sample. So then we can jump to the expected counts. So we want to say that all expected counts are greater than 5. Well, remember, you have to actually do the math. So we're going to pretend that this is all on the same page, and we're going to do the math somewhat on the actual two-way table. So go back to that two-way table. And remember the formula for expected counts? Row total times column total divided by table total. So this is going to get kind of messy, and this is where I'm going to kind of show you a couple and then just give you all, we'll just write down the numbers, and you can do it on your own if you want to make sure but I'm going to kind of create my own little column. So this is my observed. So I have 9 different observed values. And I'm going to come up with the expected. I'm just going to put E. I'm going to write an expected column for each one. So for here, I should have created my calculator earlier. I don't even think I'm going to show my work. I'm going to show you in the calculator, but just to save room and it doesn't get too messy. What was the formula? It was row total times column total divided by table total. So if I'm working with this number, what's my row total? Row is sideways, 99, times my column total, which is going down, 84. Oops, I didn't put times. And then divided by the table total, which is this corner number, 243. And you can push Control Enter to get a decimal. You should get 34.22. Remember, expected counts should be decimals. And you're going to go through and you do it for the next one. So for 39, the row is still 99. Times the column goes down to 75 divided by the table total 243. That one doesn't change. Control Enter, 30.56 if you round. And then this one, the row total is 99 times table total 80, row 99, column 84 divided by table 243, and you get 34.22. Okay, and you would keep going. So then for the 11, the row is 31 times column is 84 and divided by the table, so on, and you get 10.72. And you would keep going, so you can do this on your own. Pause the video, get your numbers, and now I'm going to go and just write the numbers so you can check. So this one should be 9.57, 10.72, and down here it should be 39.06, 34.88, and 39.06. Now, I would say if this was an AP question, somewhere, you don't necessarily have to show the work for every single expected count. You do have to list them all. But I would show the work for one, just to kind of show them that you know what you're doing. Like for that one, I know I did 99 times 84 divided by 243. Okay, so what did we want to check? What's our condition? That all these expected numbers are greater than 5, right? And our lowest is 9.57. So instead of rewriting all of those, because you did write those, as long as you listed them all out, I'm just going to say lowest expected count is 9.57, so all expected count are greater than 5. But you do need to list them somewhere on your paper, which we did on our table. Okay, so now we're ready for a do, right? So we're doing this without the calculator first, and I'm going to do another video with the calculator. So our first step for do is get your chi-square statistic, right? So to do that, you got to add up observed minus expected squared divided by expected. I should make a song or something. That's y'all can do that if you get bored at home. So the first, sorry, I gotta keep flipping. The first observed was 30, right? So we're gonna do 30 minus its expected, which is 34.22, squared divided by its expected, which is 34.22. You go with me? I know I'm talking about it's this formula. And then we're going to add, and we would do the next one. So I'm going to go ahead and show you what is it required that you write out. you have to write out the first and the last and show dot 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 in the middle. So you can write them all out if you're really doing it by hand. We would do 39 minus 30.56 squared divided by 35.6 plus, and then you do this one, you would have 9 of them. But I'm just going to put dot 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 plus, and now I'll write the last one, which would be 35 minus 39.06 squared divided by 39.06. So I encourage you to try to actually do this in your calculator by hand. Type all 9 components, write each thing you add as a component, and see if you get the same number. I'm going to save us some time in the video, but pause it here, do your own math, and see if you got this answer. It should be 18.28. So what does that mean for our chi-square distribution? That is our test statistic, 18.28, and we shade to the right. Now I probably should have put it further to the right, but what I do need to also write down is my degrees of freedom, right? So what is our formula for degrees of freedom now? Number of rows minus 1 times the number of columns minus 1. So how many rows, now not including total columns, basically how many different categories did you have of each variable? So we had 3 here and 3 here. So it's going to be 3 minus 1 times 3 minus 1, right? You had 3 different rows minus 1 times 3 different columns minus 1. So if you do that math, 2 times 2, 3 degrees of freedom is 4. Okay, so how do we find this area? Because that area is our p-value. So if you're going to find it by hand, y'all remember how to do it? See if you can figure it out on your own. You would go to chi-squared CDF, and you would put the lower bound, which is your test statistic, 18.28, your upper bound, which is infinity, and your degrees of freedom, which would be 4. And if you type that in your calculator, which it is in your notes, how to get there, you put it right here. It's under goodness of fit. You should get 0.001. So that is your p-value. So now we're ready. Once you get your p-value, you should be ready to conclude. I gotta make sure I wrap this up before 20 minutes, because the last one cut off at 20 minutes. Hopefully y'all kind of fast forward through these if you know what you're doing. Okay, so it concludes. Started this always the same way. Since p-value 0.001 is less than alpha, equaling 0.05, we, hopefully you all said reject out loud, HO, and hopefully you all said do have convincing evidence. I have to pretend y'all are here with me, or it's sad. Do have convincing evidence, and then you just write your HA, right? There is a difference. Do have convincing evidence. There is a difference in distribution of entree choice for different background music. I'm abbreviating so I don't run out of time. Which kind of matches what we thought originally when we looked at this. We saw there was a difference, but now we officially know because we did a test. So in the next video I'll do how to do it in the calculator, and we'll do an example with that.